The James Webb Space Telescope has reached its final orbit, located about 1.5 million kilometers from Earth, near the so-called L2 point, or the second Lagrange point of the Sun-Earth system. But what exactly is a Lagrange point? How many are there, and why are they so important? And why, for example, do they allow us to position a satellite in such a strategic way? Let's find out together. So, what are Lagrange points? In short, they are points in space where the gravitational interaction of two primary bodies allows a third, much less massive body to remain in equilibrium, or parked, in a fixed position relative to the other two. To better understand where Lagrange points come from, let's start with the system composed of the Earth and the Sun. As we know, the Earth orbits the Sun along an elliptical path. In reality, the two bodies, bound by gravity, orbit around the center of mass of the system, but since the Sun is much more massive than the Earth, this center of mass is located within the Sun. In effect, we can therefore consider the Earth as if it were orbiting around a fixed center. Now, let's take a third object and try to solve the equations that describe the motion of all three bodies. This is known as the three-body problem, and unfortunately, there is no general solution that can be expressed in a simple mathematical formula, as is the case with the elliptical orbits in the two-body problem. Numerical solutions can be found, but even these turn out to be chaotic. Small variations in the initial conditions of the system can lead to completely different results, making it difficult to predict the long-term behavior of a three-body system. However, there are approximate solutions to the three-body problem in particular cases. One of these special cases occurs when the third object orbits in the same plane as the other two and is much less massive, as happens, for example, with a space probe or an asteroid compared to the Earth and the Sun. In this case, the effect of the third object on the other two can be neglected, as the motion of the larger bodies is not influenced by the presence of the smaller body. This scenario is known as the restricted three-body problem, and in 1772, the mathematician Joseph Louis Lagrange, born in Turin as Giuseppe Luigi Lagrange, discovered that there are 5 points where the gravitational interaction of the two main bodies is such as to keep the third body in equilibrium. These 5 points became known as Lagrange points, although the Swiss mathematician Leonhard Euler had already discovered the first 3 of them a few years earlier. Imagine observing the Sun and the Earth from a reference system that rotates along with the Earth around the Sun, as if we were on a cosmic carousel. In this context, there are 5 points where the forces at play cancel each other out, allowing an object to remain in a fixed position relative to the other two bodies. Naturally, the object is not stationary. It orbits the Sun with the same period as the Earth and thus appears motionless relative to the Earth and the Sun if we observe it from this rotating reference system. Let's take a closer look at the Lagrange points in the Sun-Earth system. The first Lagrange point, L1, is located on the line that connects the Earth and the Sun, about 1.5 million kilometers inside Earth's orbit. An object at this position should, in theory, have a higher orbital speed than the Earth, completing an orbit around the Sun in less than a year, as the gravitational pull of the Sun is stronger. However, Earth's gravity exerts a braking effect on the object, slowing it down. If the object is exactly at the L1 point, the effect is such that it allows it to orbit the Sun at the same speed as the Earth, completing an orbit in a year. A satellite positioned at L1 will always remain in the same position relative to the Earth and the Sun, making this point ideal for studying the Sun, as it ensures an uninterrupted view of the star. Not surprisingly, the SOHO space mission, dedicated to solar observation, is positioned precisely at L1. The second Lagrange point, L2, is located about 1.5 million kilometers from Earth, but on the opposite side of L1. Here, an object experiences less gravitational pull from the Sun, which would cause it to orbit more slowly, completing an orbit in more than a year. However, Earth's gravity pulls the object toward itself, compensating for this effect and allowing the object at L2 to orbit with the same period as the Earth, maintaining a fixed position relative to our planet. L2 is an ideal position for a space observatory, as it allows constant observation of half the sky without interference from the Sun or Earth. Additionally, it is possible to easily shield the instruments from the heat and interference coming from the Sun and Earth, using a shield that can also serve as an energy source if covered with solar panels. For these reasons, L2 was chosen as the destination not only for the Webb Space Telescope but also for other space observatories, such as WMAP, Herschel, Planck, and, more recently, ESA's Gaia satellite. At this point, you might wonder how different satellites can simultaneously use the same Lagrange point. The answer is that they are not located at the exact same geometric point, but orbit around L2 in what is called a halo orbit, a stable orbit around the point. This orbit allows the satellites to maintain a relatively fixed position relative to L2, minimizing fuel consumption for orbital corrections. The third Lagrange point, L3, is located on the opposite side of the Sun relative to the Earth, and like the other points, an object positioned here orbits the Sun with the same period as the Earth, remaining always hidden behind the Sun when observed from Earth. However, L3 has little scientific utility. As an object positioned there could not transmit data back to our planet. The only practical use of L3 has been imagined in science fiction, for example, as an invisible base from Earth or as a position for a hypothetical twin planet of Earth, habitable and hidden behind the Sun. Of course, if something like this existed, we would have already noticed it thanks to observations from space probes or due to the gravitational influence it would exert on other bodies in the solar system, so it remains only a fantasy. However, the idea of a hidden planet or a secret base at L3 has captured the imagination of many science fiction writers, adding a mysterious allure to this Lagrange point. The first three Lagrange points are points of unstable equilibrium, meaning that an object placed at one of these points cannot remain there for long without corrective interventions. Any small disturbance, such as interaction with other celestial bodies, can cause it to drift away. It's like placing a ball on the top of a mountain. If it remains perfectly still, it can stay there, but a slight disturbance will make it roll away. This means that to keep a satellite at one of the first three Lagrange points, energy is needed. For example, the Webb Space Telescope has a reserve of propellant for making orbital corrections and maintaining its position around L2. However, sooner or later, the propellant will run out, thus limiting the duration of the mission. The last two Lagrange points, L4 and L5, are located along Earth's orbit in symmetrical positions, forming an equilateral triangle with the Earth and the Sun. Unlike the first 3 points, L4 and L5 are points of stable equilibrium, meaning that an object placed there tends to remain in that position, like a ball in a valley. These points are ideal for placing objects that we want to keep parked long-term, such as asteroids or satellites. In fact, the L4 and L5 points of the Sun-Jupiter system are populated by the so-called Trojan asteroids, which orbit the Sun with the same period as Jupiter. These asteroids were discovered at the beginning of the 20th century and are named after characters from Homer's Iliad. The asteroids located at L4 are called Greeks, while those at L5 are the Trojans. The stability of the L4 and L5 points has sparked the interest of scientists, who consider them possible destinations for future exploration missions and potential sites for space colonies or interplanetary refueling stations. But Lagrange points are not a phenomenon exclusive to the Sun-Earth system. They exist in any system composed of 2 celestial bodies. For example, in the Earth-Moon system, there are 5 Lagrange points, and these points are of particular interest for future space exploration. The Earth-Moon L1 point, for example, could be used as a refueling or transfer station for lunar missions, while L2 could host a telescope capable of observing the far side of the Moon or deep space without interference from Earth. Scientists are also studying the possibility of placing space telescopes or space stations at the Lagrange points of the Sun-Jupiter system, as these points offer a stable position and excellent views of the outer solar system. In conclusion, Lagrange points represent unique positions in space where the gravitational interaction between 2 primary bodies allows a third body to remain in equilibrium. These points are not only theoretically interesting but also offer extraordinary practical opportunities for exploration and observation of the cosmos. Thanks to their strategic importance for space missions, Lagrange points will continue to be crucial for our understanding of the universe and for future explorations, taking us ever farther in our journey through space. Thank you for watching. If you enjoyed the video, please leave a like and subscribe to the channel.